NetApp. Today we're going to talk about developing PMEM file system in user space. So we had the first lecture about the hardware layer, now we move to the software layer. A somewhat complex topic because talking about developing a file system over PMEM in user space. So we're going to talk about some of the stuff that we learned here at NetApp from doing this task. Specifically talk about how PMEM technology is a game changer in the field of storage in general and file system design in particular, and discuss a use case of using PMFS 2 over ZUFS 2, a technology that we developed here at NetApp and open sourced. So a few words about NetApp's usage of PMEM. We developed here a product called Max Data. About 3 years ago, NetApp acquired a small Israeli startup called Plexistore and turned the technology into a product called Max Data. Pioneer in the field, to the best of my knowledge, perhaps the only solution nowadays of a file system over persistent memory. And we did in the product, we used the Octane technology from Intel. Even though for the rest of the talk, I'm going to talk about PMEM technology in general, not specific hardware. This is public information released by NetApp, and we show a tremendous improvement in performance using Octane technology. So the Max Data itself is an enterprise-grade solution. It's proprietary, it's closed source. It's a PMEM-based file system. Being a NetApp product, it has all the features you require from a modern file system, including snapshotting and recovery and high availability. Very low latency, below 10 microseconds and millions of IOPS. And it's written in user space using a technology called ZUFS. So what is ZUFS? A year ago I gave a lecture here about ZUFS, the technology that we developed in NetApp in open source. ZUFS is a framework for developing file system in user space oriented towards PMEM-based file systems. Now you probably already know that there is a framework in the Linux kernel for developing file system in user space called Fuse. But Fuse has a few problems. First of all, it's relatively slow, as it copies data back and forth from the kernel to user space and back. And it's considered not very mature for being an enterprise-grade solution. In ZUFS, we do a different thing. We do a mechanism which allows the user space daemon, file system daemon, to map directly into the pages of the application which does the I/O, and thus reduce the need to do a copy from the kernel to user space back and forth. We write directly into the pages of the application. What we also do is, like would expect from a modern application, preserve the execution of the call on the same CPU. You cannot do it in Fuse. So the application executes a specific system call on specific CPUs. We maintain we pin the execution all the way through the user space daemon back and forth on the same CPU. I presented ZUFS a year ago, and during this year we added another extension to ZUFS which allows us to not do the copy from the user space into the application, but actually use the user space daemon as a hint, not as a hint, as a mapping layer to the kernel. We just tell the kernel, if you want to serve this I/O, go directly to the PMEM and you can find the block you are looking for at specific PMEM. This even boosts the performance even furthermore. And what's nice about ZUFS is that it's open source. The kernel part is a GPL and the user space is BSD, very liberal license. So ZUFS enough, after giving the lecture a year ago, we got a review that ZUFS enough is not enough. ZUFS as a framework is not enough and we need some kind of sample. So we decided to develop a PMFS 2 as an education file system and release it also as an open source. So first, let's go and ask ourselves, so suppose that we have a wonderful hardware, PMEM hardware, and we want to try it. We already have a DAX-based file system in the kernel, notably the ext4 and the XFS. There was historically an effort called the PMFS, which was the first attempt, as far as I know, to make a PMEM-based file system in the kernel, but it didn't mature. Later on, there was an attempt, which to the best of my knowledge is still active, but very slowly, called Nova file system. Patches were sent upstream, but never made it into the mainline kernel. And then we decided, why don't we take the PMFS, undust it, do some kind of cleanups, and do the minimal effort to port the in-kernel PMFS file system into the user space PMFS2 file system over ZUFS and see how good can it be and measure. So that's exactly what we did. Released it as a kind of educational file system which everyone who wants to play around with the technology of PMFS file system in user space can download and try himself. So PMFS is, as I said, it's an education file system. It uses the fundamental block size of 4K. It maintains its data structure at a subblock granularity, cache line aligned. The main difference is that it uses file mapping using a Radix tree instead of a traditional B tree, and a very simple mechanism for maintaining free space. I will elaborate more later on. And another technique we are using, again I will talk about it in this lecture, is that it uses a kind of SFCK to restore its free space on a mount. So before going into the detail and explaining how we did all those nice stuff, the natural question is to ask, can a user-space file system be as fast as in-kernel file system? That's the fundamental question to ask before going and implementing an entire product. And the tool used often to measure the performance of a file system in the Linux environment is using FIO. It's pretty much the de facto standard tool to measure the performance of a file system. And usually you make kind of like a throughput and latency graph. Modern machines have multiple cores, so you test it to a benchmark, say to 1, 2, 4, 8, so on CPUs, and try to figure out how good can you make a file system in user space. And we did just that. We took a server in our lab with an Optane hardware, CentOS operating system, and did some benchmark. And that's the results. Now, it's quite surprising when you think about it. A user-based file system, an educational file system, it's not an enterprise-grade solution. I will tell you that if you would put the numbers of the max data itself, you would even see better numbers. But let's take those numbers just for as an example. You can see that you can get a single-digit latency. And when you utilize the entire cores of the machine, you can go into 1 million IOPS. That's a very impressive performance for user space file systems over ZUFS using a real PMEM hardware. But the natural question to ask is, so how good is it compared to the in-kernel implementation of the XFS DAX or the ext4? So why don't we repeat the same test with those file systems? So we decided to do it. And that was a surprise. I didn't expect it. So let's zoom in for a moment. And we can see that indeed the in-kernel file system, the ext4 and the XFS DAX, when it comes to a single core and 2 cores, they outperform the PMFS2, but they don't scale out very well in terms of performance. When you increase the number of CPUs that you are using, apparently they have some kind of bottleneck. And when you use the entire in this machine, in this case 32 cores, they actually give quite poor performance. That was surprising. So to be honest, we didn't go and make a whole research what's the reason, and to be honest, we used the CentOS 7.7, so it's a relatively older kernel, so maybe if you would use the latest kernel, and don't get me wrong, those 2 file systems are excellent, they are enterprise, they are production ready, unlike the PMFS2, which is more like educational, but it shows that something is is wrong with the current implementation of file system. Now, keep in mind that those file systems were designed, well, I think the XFS is like maybe 30 years of development. They were designed from the days of HDDs, spinning Rust, and then moved to the SSD era. But they're not designed from the ground up to fit into the modern technology of PMEM hardware. We didn't do a research into the exact reasons for the performance, but we suspect it may have to do with the implementation of a journal with those file systems. And we'll talk about it right now. So the fundamental question, the observation that we have is that the PMEM technology is a paradigm shift in file system design. I actually wanted to title this slide a bit more provocative and say revolution versus evolution, because quite often when we do technology, most of the time it's actually evolution, and it's a good thing that technology evolves. But here and there, you kind of meet a new technology which requires you to shift your way of designing your software and specifically a file system. And that's if you want to take only one slide from my talk, take this one. If you're going to implement a new file system, a file system over PMEM, reconsider your assumption and don't take for granted what was assumed by previous file systems. So let's talk about the details. Okay, so some of the lessons that we learned during the development of Max Data. Again, I'm not going to talk specifically about Max Data itself. I'm talking about a more general case through the example of PMFS2. The first one is that with PMEM technology, we can do a sync operation sub-block granularity. We can actually do a cache flashing of a single cache line and say we update a timestamp of an inode. We don't have to do it in the traditional way of writing into the page cache and then flushing an entire block into the underlying device. We can actually go directly into the cache line, update the timestamp and do a CL flush, and it's there. It's much more efficient than the traditional way. Same for other elements of the file system which are below block granularity. We would like to argue that that file mapping is better done with a Radix tree than a B tree. We'll elaborate more soon. And the soft applets are preferred over journal. The common method of dealing with crash consistency is using a journal, but there's another method less known which called soft update. And I would like to argue that it's more fit into this technology. I'll elaborate more soon. As I said about the ZUFS technology, we try to maintain the execution on the same CPU. This is not specifically a PMEM related issue, but it's more like a good practice for modern hardware. And we bypass the page cache. We don't do the traditional way of file system where you write to a page cache and then flash into a storage device. Write directly into the storage device itself. Okay, so let's take two examples and put it into the details. This is actually the traditional way of doing file mapping. Basically, file system serves. This is one of the fundamentals of a file system, to serve I/O for a file. The traditional way, which most of us probably learned during university, is using an inode, an indirect inode, a double indirect inode. This was a traditional way used by the UFS and old file systems. This is actually taken from the Wikipedia page. But the more modern file system use a data structure called B tree or a B plus tree, multiple variants. This is actually the king of file mapping nowadays. But we want to argue that PMEM, we can use a better data structure, Radix tree. It's not something new, of course, but it's not commonly used in file system development. And it would be very difficult to take an existing file system which uses a B tree and make it as efficient as a Radix tree. So before we go into the details, let's just think also about what changed in file system, in file operation in general over the past 10, 15 years. Because historically, files were rather simple, right? So you had to do a write and read and truncate. And it was quite simple. But nowadays you have, in the Linux file operating system, you have more complex operation, like you have to know to seek to a data and seek all. And you have to support the entire fallocate operation, right? You have to punch a hole, collapse a range, do all kind of complex operation over, right? And you need to do it with a metadata, not the data itself. We now have the copy file range, for example, where multiple files may share the same blocks, same underlying blocks. And of course, the whole range of other file system which has to be supported. The fallocate and the copy file range really makes the entire design of a file system mapping, of a file mapping, much more complex. When you go into the detail, you will see it immediately. So how can we, so what's the advantage of using Radix tree? The main advantage is that we can only update, we don't have to update, when file is modified, we don't have to update an entire block into the file system. We can actually do atomic operation at the cache line granularity. So we can actually do some kind of pointer updates, just like we would do in memory. So in this example, we have a Radix tree with 2 levels of indirection. Typically, the lower level are the data and the higher level of fixed mapping size. And we store the height and the root LBA at the inode typically. Now, assume we want to do some kind of write operation. So we would allocate a new block, write the data, and then we would need to update the mapping. We can update a single pointer with the PMEM file system. With traditional file system, we would typically need to update an entire block and then flush it to the underlying device. But here we can do a single update. Keep in mind, I will talk about it later on, that we have to also support cache consistency upon crash. So it's not only to update the pointer, we may need to store another few bytes of information to be able to recover in case of a power failure. But the entire operation, the entire mapping metadata operation doesn't require us to do a flushing of entire blocks. We can just update single cache line at a time. Now, if we take another example using a Radix tree, more complicated, where we need to increase the tree height, this is basically the same example as before. The left side is the same before, and we add another mapping layer. Now, keep in mind that when we do those operations, not only that we can do it at the cache line granularity, updating a single pointer, until we don't update the root, we're crash consistent. Okay, even if we failed in one of those operations and crashed, we can still restore to the last known state. Okay, so this is the advantage of using Radix tree over B tree, because we can update only single pointer via a single cache line at a time, and we can do a set of atomic operations. So let's take another example, talk about crash consistency. Because one of the main problems that we have to solve in an enterprise-grade file system is how do we recover from a crash. Now, traditionally, as I showed you before, comparing the XFS and the ext to the PMEM2 file system showed some kind of bottleneck there. And I said that we suspect the bottleneck is with the journal, because in traditional file systems like the XFS and the ext, they have to maintain their consistency via a mechanism called journal. A lesser known technology is what is called soft updates, where the file system maintain its operation as a series of atomic operation, adding few bytes to each operation to be able to restore to the last known state, and flushing single operation at a time. And we can do flushing at the cache like granularity, right? We don't have to write an entire block at a time. So we would like to argue that this method is more suitable for a PMEM-based file system. It has its complexity. It's not that straightforward to craft your file system so that you will be able to recover at any time. For those of you who are familiar with file system design, just think of the states that you have to do when you do a rename. This is quite often a known issue when having a crash upon one of the operations. So you have to store with every operation not only the new pointer, but also some extra metadata to be able to recover to the last known state. Okay, so crash consistency, I would like to argue also that we can do another trick in order to have to complete the operation of crash consistency, which is more difficult to do with traditional media. PMEM is fast, which means that we can actually do a rescan of the file system upon mount, and do not upon remount, do kind of FSGK and detect the kind of failures that may have happened due to power outage, and also reconstruct the free pages upon mount, upon remount, which is something which this new technology allows us to do, and we cannot do, definitely not with magnetic drive, but also not with SSD. The third point that I'm talking here is that the ability to rescan the entire file system upon remount allows us to write a rather simple algorithm for detecting the free space. That means that we don't have to spare to have another bitmap or some kind of other complex data structure to maintain the free space. We can just simply mark all the pages as free, scan the entire file system, recover whatever is needed upon remount, and then each page which is reachable from the file system is marked as unfree or removed from the free use. So that means that when we ended the remount flow, we have on the one hand the root of the file system, which every page in the file system is reachable from the root, and on the other hand we have a queue of free pages. Okay, so we don't need to maintain a complex bitmap or whatever data structure for free pages. And last, of course, reduce the need for a journal. As I showed you before, having a journal appears to have a real performance hit for a traditional file system. That means that if one wants to redesign a file system from the ground up and use the full potential of PMEM, he has to think, how does he handle with the bottleneck of a journal? Okay, so NetApp is releasing, as I said, we don't release the source of the max data, it's a proprietary file system, but we do release a lot of information via the blog, and those of you who are interested in the technology underlying the product are more than welcome to visit the blog. Thank you.